We're going to move into research question 2 now. And this one is asking if some value of the same variable changes over time. So the example here will be using just one variable, one outcome, which is body mass index. And it's coded as body mass index 1 and 2, meaning time 1 and time 2. Now, this data has been just carried over from the example above. And the only thing that changed is we have 10 cases, 10 people, not males, not females anymore. And those 10 values that we have above are 10 of them are time 1, 10, the other 10 are time 2. In other words, we matched the two variables by hand artificially. This first record is going to be one person, and that's their BMI 1, BMI 2. So it's a fake matching. This is supposed to answer two questions in a continuous manner, whether BMI increases or decreases over time overall for this entire sample of 10 people. And using the binary coded or the categorical being overweight or not at time 1 and at time 2, we can ask the same question whether people change from one one level to the other, overweight to normal and the other way around. So we're going to start with the test of the binary changes, which is being overweight or not, time 1, time 2. And using the same logic as before, we just build a pivot table. The meaning of the pivot table here changes because now when we're reading one row, it's going to be inside the table. What we're seeing is people who change or not. So this cell in particular, column 0 and row 0, it means time 1 they were normal weight, time 2 they were also normal weight. So this one person stayed the same normal weight. In the diagonal, these three folks also stayed the same, because if we read 1 overweight initially, 1 overweight at time 2. So these three folks also stayed the same, but they were overweight all along. So the main diagonal is no changes, and the other diagonal is those who change up or down. So the main test of whether something changes here is pretty much looking at the other diagonal. This diagonal is ignored. And the test is different. It's not a plain chi-square test. It's called the McNemar test, but we implemented it here by hand too. And it uses the same observed values inside this cross table. And it provides a chi-square value and a p-value, just like above. The logic is slightly different though. I'm just going to move to show the formula for this McNemar test, and then to show where we implemented it. But it's pretty much, when we implement this formula, it's looking at the values in the other diagonal, which is people who change. And we just had to adjust this one value in one of the cells, because sometimes it does happen that there is a 0 in the table. And that's a problem. So 0 cannot be handled well. So you have to do something. We fixed it. But pretty much we're looking at to the extent to which people who change up are more than people who change down. That's all there is. And the other ones are kind of ignored. This test is giving a value which is pretty high. And we don't have the critical value here, but for degrees of freedom 1, we remember from above is 3.8. So it is larger than 3.8. And this is also shown in the p-value. So it means the p-value is significant. That's an error here. So it's less than 0.05. And it means that there is actually a change here that we observe. So we see a change from pre to post in being overweight or not. These and folks do change over time. There is another way to answer the same question, which is by looking at the continuous BMI, BMI time 1, BMI time 2, which is these two values. These are the means at time 1 and at time 2. And if you look above at the previous test, they are the same value because we use the same two variables. But now, compared to the test above, this is the t-test for paired samples. In other words, there is one sample with paired values, time 1, time 2. The question is whether these change their continuous BMI or body mass index level. And if we just jump to the conclusion, but everything is implemented already, we can see that there is a change, there is a significant change, meaning the p-value is small. In other words, there is an average change between time 1 and time 2 in BMI. It's actually a decrease the way we see it here. But everything is implemented in here. I'm just going to mention one more thing, but it's very quickly. For those who want to test the same thing in a different manner, it can be tested in a free software online, which is Onyx, as a model of latent change. But it's very easy to be done.
And just a quick summary of that. So the first was the McNemar's test, which is best used for dichotomous paired nominal data, which is what we had there. And then, as you could tell, the paired t-test, which we did after, is used for paired continuous data. One that we didn't mention was the Wilcoxon sign rank test, which can be used for non-normally distributed paired continuous or ordinal data. And one of the advantages of the McNemar's test, which we used first, is that it doesn't require the assumption of normality, whereas the paired t-test does have that assumption attached to it.
Thank you. Yeah, that's great. There are many tests available out there, and some are more appropriate than others in some instances. That's a good point. It's what we're showing here is the first steps into testing. But yes, in some cases, these tests may need to be adjusted or abandoned, and better ones should be looked at.
Absolutely. And always check the assumptions before you use a certain test.
That's right. There are a number of assumptions even coming into this last section, which is research question 3. So in here, we are going to use two variables, which are two different variables. So it's a sample of 10 people, and they have values for BMI and for this A1C, which is hemoglobin A1C, which is a measure of blood glucose. And whenever we have two variables like this, a natural question is whether the two go hand in hand or not. And the way to clarify this question and what methods we can use to answer the question, and then what assumptions we can rest on when we use the different methods, is the best way is to look at the scatter plot, meaning the graph of the actual two sets of values. And we're showing here BMI on the horizontal and A1C on the vertical axis. And this is generated data, but again, it's generated based on the raw data in another worksheet in here. And we just split this graph by adding two lines, a horizontal line that's crossing the entire graph at the mean level of A1C, and the vertical line that's going at the mean level of BMI. So this one pretty much splits the graph into 4 quadrants. And just as a general visual rule to interpret this concept of association and correlation, if all of these 10 dots, which we are seeing here in the graph, were distributed all over the place randomly, there wouldn't be any relationship to talk about. Now, if most of them are distributed in this quadrant upright, which is quadrant 3, and the other one diagonally opposed, quadrant 1, so if most dots were up and down this way on a diagonal, that would indicate there is some going hand in hand or correlation, but a positive one, meaning lower values of BMI are also seen with lower values in A1C, that's this quadrant, and higher values of BMI to the right are also having higher values of A1C, which is upper or above the mean value. So that would be a positive correlation. The other one would be a negative correlation. This happens to be a logic that applies also to the chi-square test we talked about above. Sorry. And it means pretty much that we have 4 categories of people or values or cross values pretty much. One going hand in hand with the other one. High and high levels here, low and low levels in the opposite one, and then high, low, low, high. And the test that we're going to implement here is going to just say to what extent there is evidence that these are related, that they are not just 2 random variables. So the way to test this is to look at the correlation. That's the simplest concept. And there is a way to get it in Excel very simply, which is just apply this formula, which is correlation, correl. And you just have to enter the 2 columns and it gives you the value. The only problem is it doesn't test whether this is a significantly different from 0 correlation or not. So we should actually test if this value is or not different from 0, and that's by using a t-test of this correlation value. There is a formula you can look up online, but just by looking at the value of the t-test for the correlation coefficient, which is small here, it's 0.5, 0.6, and comparing it to a critical value, it's clear that this is not a significantly different from 0 correlation. So even though this appears to be a sizable number, 0.2, in a range of -1 to +1, it's not that small. It is smallish. It's not actually significantly different. 0. The same test can be implemented by analyzing it as a regression model. Again, we're coming back to the issue of assumptions. Linear regression has a number of assumptions that it rests on. There's a screenshot here on how to run it in Excel directly. But if we believe the assumptions behind this regression model, then the coefficient for X variable, which is the predictor, looking at the p-value straight away, seems to say that it's almost 0. It's null, or it's statistically 0. So the conclusion pretty much is that the predictor, or A1C, actually was the other way around. The BMI does not predict A1C, but they are not related. And that's a good point here too. In a regression model, you can regress either one or on the other one. So there is going to be a regression coefficient if you regress BMI on A1C, and another regression coefficient if you flip them. And the correlation coefficient and the covariance are going to be the same. These are bidirectional kind of statistics. And the only other comment would be that the original scatter plot of the full data set is shown in here, which does not indicate a relationship by looking at the quadrants, the 4 quadrants visually, but we're not testing it here. So this is supposed to be the end of this session.
Absolutely. And if you have any questions about the things that we've discussed during this video, please leave a comment with your question, and we would love to address it either in text or over a next video. So thank you for your attention, and we hope to continue this series.
Thank you.